So, welcome to the start of the Year 2 Applied Maths course, and we're going to begin with some statistics. So, Chapter 1 is going to continue from what you learned during Year 1 in Chapter 4, and we're working on the ideas of regression and correlation. So, we're talking about bivariate data. Bivariate means we have two variables that we are dealing with. Let's call them X and Y, and we're looking for a correlation between those two variables. So at GCSE, you met this when you studied scatter graphs. And when you studied scatter graphs, you tried to fit something called a line of best fit to your scatter graph. At A-level, we call this a regression line, but we call it a regression line specifically when we are looking for a straight line of best fit. So we are looking for, with regression, what's called a linear correlation. Linear meaning a straight line correlation. Because data can fit all sorts of patterns and all sorts of relationships, and these don't need to be straight or linear. They could take all sorts of other shapes as well. Now, the thing is, we have lovely statistical ways of measuring the correlation of the data if the correlation is linear. If it's not linear, things aren't quite so straightforward. So in the next video, we're going to look at a way that we can quantify numerically the correlation, the linear correlation between two sets of data. But before we do that, we're going to look at a way of taking data that fits other patterns and turning it into a linear correlation or a linear pattern so that we can analyse it with the maths we're going to learn about later on in the chapter. So you also learnt, this feeds into what we're about to do, in your pure course last year, you learnt in chapter 14 about exponential models. You learnt how you can take data that fits a curve, either a polynomial curve where something like x squared or x cubed, or an exponential curve, something like 2 to the power of x or e to the power of x. And you learnt how you can use logarithms to turn those into straight lines. And that's what we're going to apply here. So we're going to take data that fits some kind of curved relationship and we're going to linearize it using logarithms. This is a process that's used a lot in statistics. You will see very often when large data sets are shared on the television, you'll see graphs that use what's called a logarithmic scale, either on the x-axis or the y-axis or both. And these logarithmic scales are used specifically to turn curved relationships into linear ones so that they're easier to analyse. So let's look at the two different types that we're going to deal with here. First of all, you might have data that fits some kind of polynomial curve. So let's take something that looks a bit like this, and that looks maybe like it fits perhaps a quadratic or a section of a cubic maybe. Generally, what we're saying is that if your data fits this kind of curve, x to the power of n, but of course maybe some multiple of it, maybe it's been stretched. If it fits this form, then we can turn this into a linear relationship by taking logarithms of both sides. So let's do that. Now let's apply our laws of logarithms to the right-hand side. Because these two are multiplied together, we can split them into two separate logarithms with addition. Now let's apply the laws of logarithms here. This n becomes a multiple of log x. Now look at the form this takes. This is a straight line because here we have a variable. Let's call that capital Y. Here we have another variable. Let's call that capital X. Now a was a constant in the original equation, which means log a will also be a constant. So let's just call it that for now. N was a constant. If this was a quadratic, n would be 2. If it were a cubic, n would be 3. That number there is constant. So it's still a constant here. So let's call it that. And you can see that although our variables are logarithmic, they fit a linear form. So we could plot log y against log x, and this data would form a straight line. Now we don't have to do it for polynomial data, we could do it for data that have an exponential relationship. Now we know exponential relationships are those where the data can grow very fast. So maybe something like that, and you might think, oh, I think an exponential relationship fits better than a polynomial one. So if that's the case, your exponential relationship will be something of this form. A number to the power of x, but your variable is up in the power, like 2 to the power of x or e to the power of x. And you might have some kind of stretch of that. So we've got another constant there, a. Now we're going to apply the same process. We're going to take logarithms of both sides. Now apply the laws of logarithms to the right. And again. And now let's analyse it. Let's look carefully. This is variable and this is variable. So let's call that one capital Y. Let's call that one capital X. However, this is constant because A was initially constant and B was initially constant. So this is constant here. So yet again, we have something in a linear form. But be very careful about what changes. If you have something in a polynomial form, then you take logs of x and y. If you have something in an exponential form, you take logs of y, but you don't take logs of x. X remains the same. And by doing that process, either taking logs of x and y, or by taking a log of y and keeping x the same, you turn something that fits a curved pattern into something that fits a straight line. So both of these, if I had data in front of me and I were to plot log y against x here or log y against log x here, they wouldn't look curved, they would look straight. And you can see an example of that in your book on page 2. Now let's have a look at example 1. So in example 1, we have a table here. I've not put the table on here, but the table's in the book for you to look at, and it shows the temperature of a colony of bacteria and some measure called G of the rate of growth. So the rate of growth talking about how much it's growing over time. Now it tells us that these data are coded, so straight away, and it's coded using logarithms, so straight away we know that these data fit some kind of curve, either polynomial or exponential. Now they're coded using logarithms. X is used in place of t, so there's no logs taken there. Y is used in place of log g. So think about which of these two forms it fits. We're not taking logarithms of t. So that's this form here, where you keep your x variable the same, but you take logs with your y variable. So we know that the original data must have fit an exponential curve. Now let's have a look at this. The regression line of the coded data is this. Y equals minus 0.2215. So thinking about a straight line, that's going to be our y-intercept, plus 0.0792x. And 0.0792 there would be the gradient of the line. Now in part A, it says that Mika thinks that this constant here, this minus 0.2215, that shows that when the temperature is 0, the colony is shrinking. So what's going on here is we've got a straight line, temperature is the same as x, so they're saying when x is 0 or t is 0, well, that bit will go, the y value will be this, minus 0.2215. So they're saying, that shows that your growth rate, which is related to y, is shrinking because that's negative. But that would be wrong. Let's have a look at why that would be wrong. Let's replace y and x with what they are when they're coded. So y is log g. and x is t. So when they're not coded, we have this going on. Now, we're talking about when t is 0. So let's make that 0. And we've got log g equals minus 0.2215. Now this is a log base 10. So when we find g on its own, we do 10 to the power of the other side. Let's work that out. 10 to the power of minus 0.2215. That's 0.600 to 3 significant figures. Now, what does that mean? That means that when t is 0, the growth rate is 0.6, which is positive. So the colony isn't shrinking, the colony is growing when the temperature is 0. So in part B, it asks us now to work out the actual equation in terms of g and t for these data. So it wants us to work out the original exponential equation. We're going to do the same thing as we did in the start of this question here. We're going to take our straight line and we're going to replace y with log g. And we're going to replace x with t. And that's because this is what we're told here was the original coding. Now what we want to do is make g the subject of this. So because this is a log base 10, we're going to do 10 to the power of the other side. Now be careful here. The whole of the right hand side is going to go up into the index. And now you need to apply your laws of indices kind of in reverse. So think about this for a second. If you have x to the power of a times x to the power of b, we know that that can be written as x to the power of a plus b. So if you see two things being added in your index, you can split this whole thing up into x to the power of the first times x to the power of the second. And apply that here, that means we've got 10 to the power of the first times 10 to the power of the second. Now let's make these numbers nicer. Let's put them into 3 significant figures. We already know this first one. We worked out this one here in part A, so we know that's 0.600. Now let's work out this one. So 10 to the power of 0.0792 is 1.20 to 3 significant figures. To the power of t. So this is our exponential relationship. G equals 0.600 times by 1.20 to the t. So this is an exponential curve where we're basing on this 1.20 to the power of t, and then this is the vertical stretch scale factor. Now if we needed to, we're told in the question that we're asked to find this equation in the form G equals kb to the t, where k and b are the constants to be found. So what we know is that k is 0.600 and b is 1.20. So have a go at exercise 1a, and in the next video we're going to look at the idea of correlation in a bit more detail.